Today we're going to look at Lewis diagrams and electron-dot diagrams of molecules and also of a formula unit. So we're going to start off looking at diagrams for hydrides of carbon, nitrogen, oxygen and chlorine. And so you've got the formulas there because you have to know the formulas before you start. And the electron-dot diagrams will show shared pairs of electrons, the bonds between atoms, and the unshared pairs of valence electrons that aren't taking part in bonding. You can also make models. Here are the sort of standard colours of particular atoms, mainly because as you buy kits, they have the right number of links to put bonds in, or indeed lone pairs. So we're going to write the formula for each hydride, going to make models of them to see what we've got. We're going to draw the Lewis structure using the number of valence electrons around each of the contributing atoms, and put covalent bonds between the atom and hydrogen, and with a shared pair of electrons in the covalent bond, one from each of the contributory atoms. So just looking at this, knowing the combining power, the valency of the electrons, in red at the top you're given the valences, the major valencies of elements in those groups. In some cases it's the only valency in that particular vertical column, and the number of valence electrons for the first four groups is the same as the valency, and then it's 8 minus the number of valence electrons to give you the valency. And so we've got the non-metal metal boundary that is there. So if we're looking at nitrogen, it's in group 15, 5 valence electrons and a valency of 3, combining power of 3. Carbon is in group 14, 4 valence electrons and a valency of 4. And we're going to use the valency of hydrogen, which is 1. There's a single electron in the outer shell, the only shell of hydrogen, and look at the valency of the other element which is joined in the compound. So here's hydrogen with the nucleus with the H in and the valence electron, and here's carbon, 4 valence electrons, and it also has 2 other electrons in an inner shell which aren't taking part in bonding. And there's hydrogen again on the right, and pause while you answer how many hydrogen atoms we'll need to combine with the carbon atom to make a stable octet of 8 electrons with sharing. So here in the diagram, the bottom right, you'll see that indeed there are 4 around there, and the formula will be CH4, and each bond, covalent bond, is made up of 1 electron from the valence shell of a hydrogen atom and 1 of the electrons in the valence shell of the carbon atom. And the Lewis diagrams, you can draw a line for those shared pair for the covalent bonds and just put in the symbols. You don't need the circles. And methane is in a lot of places, can bubble out of various parts of rotting vegetation in bogs and heavily waterlogged areas, and here methane lakes on Titan, one of Saturn's moons, and hydrogen combining with nitrogen. So think about nitrogen's valency, go back a few slides if you need to, And how many valence electrons does it have? Group 15 has 5, nitrogen only has 1, and as they join together, each nitrogen-hydrogen bond has that shared pair of electrons in the covalent bond, one from nitrogen and one from one of the hydrogen atoms. And the nitrogen, with 3 hydrogen atoms bonded, has 8 electrons in the valence shell. There is also a lone pair of electrons. That's going to affect the shape. The stability is there with it because nitrogen has its full outer shell once it's sharing 3 electrons with the 3 contributing hydrogen atoms. And then drawing lines in for the shared pairs for the covalent bonds, and ammonia is NH3. And so we can draw them in different ways and pause to look more closely at these. And then if we're going to look at hydrogen combining with hydrogen, diatomic gas, the Space Shuttle main engine burns liquid hydrogen with liquid nitrogen. And here we have 2 hydrogen atoms, each with a single valence electron, and when they're shared, you've got the covalent bond, the line, which is made up of those 2 electrons. And then if we look at oxygen, having 6 valence electrons, how many hydrogens are going to combine with each oxygen atom? And pause while you think about that answer. So we're going to want oxygen to have an octet. So oxygen with 6 valence electrons needs to share 2 electrons, one from each of 2 hydrogen atoms. And here's its structure that you see here, and then drawn with the actual line representing the shared pair in the covalent bond, or here just with letters, but still showing the lone pairs of electrons which have an effect on the shape of the molecule, which we'll discover later. Another compound between hydrogen and oxygen is hydrogen peroxide. So you've got an oxygen-oxygen link in there as well. Both of the oxygen atoms achieve that octet with 8 electrons after bonding with 2 hydrogens, and obviously the link between the oxygens. And here's the Lewis diagram with the lines for the bonds, and the hydrogen peroxide is the oxidizing agent in the fuel in a mercury capsule. And then looking at hydrogen with chlorine, chlorine has 7 valence electrons, and so we only need 1 hydrogen to complete chlorine's octet, and these are ways of drawing the Lewis structure with the line representing the covalent bond. And out of interest, here's glucose, and lots of unshared pairs on the oxygen. Carbon, the black spheres there, all have a valency of 4. The white spheres are hydrogen, and you can see all of the covalent bonds because those are the lines between each of the atoms. And then we're going to look at sodium hydride, but previous examples, which include methane, ammonia, water and hydrogen chloride, are combinations of non-metallic elements and covalently bonded. Sodium hydride is a metal and a non-metal combined. It's going to be an ionic compound, and the Lewis structure is going to be a little bit different. And the metal atoms lose valence electrons and form positive ions. The non-metals gain electrons, become negative ions. So look at the red writing there with the examples. And so when we're looking at the electron arrangement of a sodium atom, 281, it's got a single electron in the valence shell, and when it becomes a sodium ion, it has lost that electron to the other atom in the ionic compound. Hydrogen atom starts off as a neutral atom, 1 proton, 1 electron, and then when it becomes a hydride ion, the hydrogen atom gains an electron here from the sodium atom and has a negative charge. And so the sodium atom becomes a sodium ion, the hydrogen atom becomes the hydride ion, and the sodium still has the 2 and the 8 full shells, but it's lost the valence shell. And the hydrogen atom with 1 electron has gained 1 and now has a full outer shell, because that first shell can only contain 2 electrons. And then to write the Lewis structure for ionic compounds, you put the symbols in the square brackets, you put the charges outside, and you show the number of electrons in the valence shell. Sodium has lost its 1 electron, so you don't show any dots around the sodium. The hydrogen, which had 1 electron, has now gained another and has a negative charge, so you see the 2 dots representing the electrons in the hydride ion. And a pause to review the rules of Lewis diagrams, how to use the valence shells to do that. And we'll just look at an example here with sulfur trioxide. So you're going to sum the valence electrons of all the atoms. Sulfur has 6 valence electrons, oxygen also has 6. So the total is going to be 6 from sulfur and 3 times 6 from oxygen, making 24 valence electrons in all. Choose the central atom here where there's only 1 of them, and assign pairs of electrons to make each bond, and that's going to be 2 electrons. You've got 3 bonds, so as we've drawn it here, there are 6 electrons that have been used, which are out of the 24 leaves 18. So if we assign the 18 electrons, right, let's put them around each of the oxygens, that looks really very, very good, but falls short in 2 areas. The first one is it leaves sulfur, period 3 element, with 6 electrons, so it is not an octet. The second thing is oxygen had 6 electrons to start with, so there's 6 red dots around each one, which then implies each of the bonds are dative coordinate bonds where the sulfur atom is contributing both of them. But if we satisfy the octet rules, and because sulfur is in period 3 and ones that higher period numbers, they're large enough, you can have extended octets, and that's what you have here, with 2 lone pairs on each of the oxygen atoms and a bond between each, a double bond between each of the oxygens with the sulfur. And pause here to draw the Lewis structures of hydrogen fluoride, nitrogen, and carbon tetrafluoride. So pause until you've completed all of those. And check what you've done. Look at the valence electrons, look at the number of bonds, each made up of 2 electrons, and where you're putting the unshared. So just pause to read through that one. And then nitrogen, the diagram number 1 on the right is showing the valence electrons on nitrogen, joining the two together with a single bond, and that will leave nitrogen, each of the nitrogens, with 6 electrons, so not a stable octet. And we need to use 4 more electrons, so it's going to be a double bond, 2 more bonds added to make a triple bond between the nitrogen atoms, and a single unshared pair of electrons on each nitrogen atom. And here's CF4. Pause to read through that. Again, the valence electrons and the bonds, so how many are left to be unshared pairs. And again, pause the video, because I want you to explain these diagrams using the terms valence electrons, bond pairs, unshared pairs of electrons. And when you've done that for each of them, continue, and again another pause to answer the question, how do you think the Lewis diagram helps to describe the shapes of molecules? And so essentially, what would the shape of CF4 be, and a little bit more complicated PF5, but we're going to go on to look at shapes of molecules. But how does the Lewis diagram help to describe them? And my hint will be they aren't planar. So many thanks to Washington International School and WIS Chemistry.